On July 1st, 2025, at precisely 14 hours, 37 minutes Universal Time, an automated telescope in Chile detected something that would ignite imaginations worldwide. The Atlas survey system, designed to hunt potentially hazardous asteroids, flagged an object moving too fast to be from our solar system. Within hours, calculations confirmed what seemed impossible. This visitor came from another star. They designated it 3I/ATLAS, the third confirmed interstellar object after Oumuamua and Borisov. But unlike its predecessors, this cosmic wanderer would spawn rumors that spread faster than its incredible velocity of 209,000 kilometers per hour. The initial observations seemed routine, a faint smudge against the star field, moving at 4.5 astronomical units from our sun. Astronomers worldwide turned their instruments toward this interstellar visitor, expecting to gather straightforward data about its composition and trajectory. They got far more than they bargained for. Within days, something peculiar emerged from the spectroscopic data. This wasn't behaving like any comet in our catalogues. The Gemini North Telescope revealed an active coma, a cloud of gas and dust, but its chemistry defied expectations. Where water should dominate, carbon dioxide reigned supreme, an 8-to-1 ratio that shouldn't exist. Think of it this way: if normal comets breathe water vapor, 3I/ATLAS was exhaling pure carbon dioxide. It was like finding a fish that breathed air, or a bird that swam but couldn't fly. The anomaly demanded explanation. Social media lit up with speculation. Amateur astronomers shared pixelated images. Science communicators struggled to explain the chemistry. And somewhere in that digital telephone game, a rumor was born. What if it wasn't natural? The European Space Agency coordinated global tracking efforts. NASA marshaled its most powerful instruments: Hubble, James Webb, Swift. Every major observatory on Earth joined what became humanity's most intensive study of a single small object. The more they looked, the stranger it seemed. The carbon dioxide cloud extended 348,000 kilometers from the nucleus. To put that in perspective, you could fit the entire Earth-Moon system inside it with room to spare. How could something only a few kilometers across create such an enormous envelope of gas? Natural processes seemed inadequate. Radio telescopes joined the observation campaign, and this is where the story takes its controversial turn. When instruments designed to detect the faintest whispers from space pointed at 3I/ATLAS, operators noticed something in the static. Not a clear signal, nothing that obvious, but patterns in the noise that seemed almost too regular. The human brain excels at finding patterns, even where none exist. We see faces in clouds, hear voices in white noise, and when you're looking at data from an object that already defies explanation, it's easy to see what you want to see. Radio astronomers knew this. They'd been fooled before. The WOW signal of 1977 had taught them caution. Pulsars in the 1960s had briefly been labeled LGM for little green men before their natural origin was understood. The scientific community had protocols for this exact situation. If 3I/ATLAS was transmitting artificial signals, there were procedures to follow, verification steps that couldn't be rushed. SETI, the Search for Extraterrestrial Intelligence, turned their specialized equipment toward the visitor. Their receivers, designed specifically to detect artificial transmissions, began their careful analysis. What they found would either change history or add another chapter to the long book of false alarms. But then radio astronomers noticed something that made even skeptics pause. The frequency of the supposed patterns was eerily close to 1420 megahertz, the hydrogen line, the universal frequency that many scientists believed alien civilizations would use for communication. Radio telescopes don't actually listen to space in the way our ears hear sound. They detect electromagnetic radiation at frequencies far below what human senses can perceive. When pointed at 3I/ATLAS, these instruments picked up exactly what scientists expected from a comet warming in sunlight: the radio signature of ionized gas and dust. In simple terms, as solar radiation strikes the comet's expelled material, it strips electrons from atoms, creating charged particles. These ions emit radio waves as they recombine with electrons, a completely natural process that occurs in every active comet. The emissions create a kind of cosmic static, random noise spread across multiple frequencies. But here's where interpretation becomes tricky. When you record hours of this static and analyze it with sophisticated software, patterns can emerge from pure randomness. It's like staring at television snow long enough. Eventually, your brain starts seeing shapes that aren't really there. The frequency near 1420 MHz sparked particular interest. This is the hydrogen line, caused by the universe's most abundant element flipping its electron spin. Scientists have long theorized that intelligent civilizations might broadcast at this frequency because any technologically capable species would recognize its significance. Finding emissions near this frequency from an interstellar object was tantalizingly coincidental. Dr. Sarah Chen at the Green Bank Observatory ran the signals through standard SETI protocols. These procedures, refined over decades, can distinguish between artificial narrowband signals and natural broadband emissions. The analysis requires checking for Doppler shift consistency, signal bandwidth, and modulation patterns that would indicate information content. The results were definitive but disappointing for those hoping for alien contact. The emissions showed typical broadband characteristics of natural plasma interactions. No narrowband carriers, no mathematical patterns, no modulation that could carry information. Just cosmic noise, albeit from an unusual source. Think of it this way. A campfire produces light, but it's not sending Morse code. The flickering might randomly create patterns that look meaningful, but they're just the chaos of combustion. 3. I/ATLAS's radio emissions were the electromagnetic equivalent of that flickering flame. The natural emissions were actually fascinating in their own right. The intensity and distribution told scientists about the density of ionized material in the coma. Combined with optical observations, these measurements helped researchers understand how this interstellar visitor was shedding material as it approached our Sun. Radio astronomers use a technique called interferometry, combining signals from multiple telescopes to create a virtual dish sometimes as large as Earth itself. When this technique was applied to 3 I/ATLAS, it revealed the three-dimensional structure of the ionized gas cloud. The shape was consistent with solar-wind interaction, not artificial transmission patterns. Dr. James Rodriguez at the Very Large Array explained it clearly. If 3 I/ATLAS were broadcasting, we'd see it immediately. Artificial signals stand out like a lighthouse in fog. What we're seeing is more like moonlight on choppy water, natural, random reflections. The media, however, had already run with the story. Headlines proclaimed, "Mysterious signals from interstellar visitor and scientists detect patterns in alien objects' emissions." The careful qualifications and natural explanations were buried in later paragraphs, if mentioned at all. Professional radio astronomers found themselves in a familiar position, explaining why exciting-sounding observations were actually mundane. They'd done this dance before with pulsars, fast radio bursts, and dozens of other phenomena that seemed artificial until understood. SETI Institute protocols require any potential artificial signal to be independently verified by multiple observatories. For 3 I/ATLAS, observatories on 6 continents pointed their dishes at the visitor. Every single one detected the same natural broadband emissions. No structured signals, no information content, no evidence of technology. The frequency was almost too perfect, if you wanted it to be. The numbers surrounding 3 I/ATLAS read like a cosmic challenge to human understanding. At 209,000 kilometers per hour, this visitor moves faster than any natural object we've tracked through our solar system. To grasp this velocity, consider that it could circle Earth's equator in under 12 minutes. This isn't just fast, It's impossibly fast for anything originating in our cosmic neighborhood. The mathematical proof of its interstellar origin lies in something called orbital eccentricity. Objects bound to our Sun have eccentricity values less than 1, meaning they follow closed elliptical paths. 3I/ATLAS has an eccentricity of 1.06, confirming a hyperbolic trajectory that will never return. It's passing through our solar system once, like a cosmic bullet fired from an unimaginable distance. This extreme velocity creates a psychological effect. When something moves this fast and comes from so far away, our pattern-seeking minds immediately jump to artificial explanations. Surely something this unusual must be engineered. The math seems too perfect, too precise. Dr. Michael Torres at MIT calculated the object's past trajectory, tracing its path backward through space and time. The results suggested an origin in the galaxy's thick disk, a population of stars that formed 8 to 12 billion years ago. 3I/ATLAS had been wandering the galaxy since before our Sun was born. Think about that timeline. This object has been traveling through interstellar space for longer than Earth has existed. During its journey, entire stellar generations have been born and died. Planets have formed and potentially evolved life. Civilizations might have risen and fallen. Yet 3I/ATLAS continued its silent voyage, finally arriving at our doorstep in 2025. The trajectory analysis revealed another unsettling detail. 3I/ATLAS would pass through our inner solar system with remarkable precision, threading between planetary orbits like a needle through cosmic cloth. Its closest approach to Earth, 1.88 astronomical units, about 281 million kilometers. Safe, but suspiciously optimal for observation from our planet. Human psychology plays tricks with large numbers and vast timescales. We're not equipped to truly comprehend billions of years or hundreds of millions of kilometers, so we reduce them to patterns we can understand, often seeing design where only chance exists. The Discovery statistics add another layer to the mystery. In nearly a decade of operation, the ATLAS survey system had catalogued hundreds of thousands of objects. It found exactly one interstellar visitor. The rarity, perhaps 1 in a million objects, makes 3I/ATLAS feel special, chosen, meaningful. But astronomers understand that rare doesn't mean artificial. The galaxy contains trillions of wandering objects ejected from planetary systems during their chaotic formation. We detect so few simply because space is vast and these objects are small and dark. Finding one is like spotting a specific grain of sand on a beach at night using only a penlight. The mathematical models of planetary system formation predict exactly this kind of debris. When Jupiter-sized planets migrate through young solar systems, they scatter smaller bodies like cosmic pinballs. Most fall into their parent star or get absorbed by planets. But some achieve escape velocity, beginning epic journeys between the stars. 3I/ATLAS's velocity components tell us about its stellar neighborhood of origin. Its motion relative to the local standard of rest, how stars in our region typically move, suggests it came from an older, dynamically heated population. These are stars that have been gravitationally stirred over billions of years, their orbits made chaotic by repeated encounters. The numbers create an illusion of intention that doesn't exist. Yes, the trajectory is remarkable. Yes, the velocity is extreme. Yes, the timing seems coincidental. But the universe is vast enough that even 1,000,000 to 1 chances happen regularly. 3 previous visitors, 3 different stories, each challenging our assumptions in unique ways. The chemistry of 3I/ATLAS defies every model we've built about how comets should behave. Where normal comets release primarily water vapor when heated by the sun, this visitor breathes out carbon dioxide in proportions that shouldn't exist. The ratio, 8 parts CO2 to 1 part water, is completely reversed from what we see in our solar system. The James Webb Space Telescope captured this chemical signature on August 6, 2025, its infrared sensors detecting molecular fingerprints with unprecedented precision. The Discovery team triple-checked their data, ran calibration tests, and compared results with other instruments. The conclusion remained unchanged. 3I/ATLAS was chemically alien. To understand why this matters, consider how comets form. In the cold outer regions of stellar systems, various molecules freeze into ice at different distances from the parent star. Water freezes first, then carbon dioxide, then carbon monoxide, creating distinct zones of chemical composition. An object's ice content tells us where it formed. Most solar system comets formed beyond the water frost line, incorporating primarily water ice with smaller amounts of other volatiles. But 3I/ATLAS seems to have formed in a bizarre environment where carbon dioxide dominated. Perhaps near a CO2 frost line, but inside the water line. Such conditions might exist in other stellar systems, but not in ours. Dr. Lisa Park at Caltech proposed several explanations. Maybe 3I/ATLAS formed around a star with unusual carbon to oxygen ratios. Perhaps it experienced chemical processing during its billions of years in interstellar space. Or it could represent material from a type of protoplanetary disk we've never observed. The Spitzer observations added another puzzle piece. The carbon dioxide wasn't confined to a small region near the nucleus. Instead, it extended outward for 348,000 kilometers, larger than the distance between Earth and the Moon. How could a nucleus only a few kilometers across maintain such an enormous cloud of gas? Think of it like a tiny air freshener filling an entire stadium with scent. The physics doesn't add up unless something unusual is happening. Either the nucleus is extraordinarily active, or carbon dioxide is being produced through mechanisms we don't understand. Natural explanations exist, but stretch credibility. Perhaps 3I/ATLAS is fragmenting, with multiple pieces contributing to the gas cloud. Maybe pockets of super-volatile CO2 are exploding as they warm, creating jets that extend far beyond typical cometary activity. Or the extended cloud might result from a recent collision that scattered CO2-rich material across a vast volume. The spectroscopic data revealed something else peculiar. While JWST detected abundant CO2 gas, Spitzer found evidence of water ice on the surface. The water was there, but wasn't sublimating efficiently. Something was suppressing water vapor while allowing CO2 to escape freely. Laboratory experiments with analog materials suggest one possibility. If 3I/ATLAS developed an insulating crust during its interstellar journey, a layer of processed organics and dust, it might trap water vapor while allowing more volatile CO2 to percolate through cracks. It's like a coffee filter that blocks grounds but lets liquid through. The temperature profile supports this hypothesis. At 3I/ATLAS's current distance from the Sun, CO2. Sublimation is efficient, while water ice remains mostly frozen. As it approaches perihelion, we should see the chemistry change if natural thermal processes are responsible. But some researchers whispered about less conventional possibilities. What if the chemistry was intentionally engineered? What if something was actively converting water to CO2? These ideas remained on the fringes, unsupported by evidence, but impossible to completely dismiss. The carbon dioxide enigma forces us to reconsider our assumptions about planetary formation across the galaxy. If objects like 3I/ATLAS are common, then stellar systems must create a wider variety of chemical environments than we imagined. SETI turned their dishes toward it, hoping to find answers in radio waves rather than molecules. The search for extraterrestrial intelligence operates on a simple premise. If technological civilizations exist, they should produce detectable signals that stand out from natural cosmic noise. When 3I/ATLAS arrived with its unusual chemistry and interstellar origin, SETI researchers saw an opportunity to test this premise on an object that had traveled between stars. SETI protocols, refined over 6 decades, are surprisingly straightforward. Look for narrowband signals, transmissions confined to a tiny slice of the electromagnetic spectrum. Natural processes produce broadband emissions spread across many frequencies, like static on an old radio. Artificial signals concentrate power in specific frequencies, like a radio station's carrier wave. Dr. Rebecca Martinez at the SETI Institute explained their approach. We're not looking for messages or alien music. We're looking for any signal that physics says nature can't produce. A single monotone beep would be enough to change everything. The Allen Telescope Array in California, designed specifically for SETI observations, pointed its 42 dishes at 3I/A TLAS within days of discovery. The system can monitor millions of frequency channels simultaneously, searching for the electronic needle in the cosmic haystack. If the visitor was transmitting, even accidentally, they would detect it. Think of SETI like a cosmic wiretap. The instruments don't need to decode alien messages or understand alien technology. They just need to detect electromagnetic signatures that can't arise from natural processes. It's pattern recognition at its most fundamental level. The verification protocols are rigorous to the point of paranoia. Any interesting signal must pass multiple tests. First, it must persist when the telescope tracks the target. Second, it must disappear when pointing away, confirming the source direction. Third, it must be detected by independent observatories to rule out local interference. For 3I/ATLAS, SETI ran through their entire detection pipeline. They searched for continuous waves, pulse signals, and frequency-modulated transmissions. They looked for signals that might be Doppler shifted by the object's motion. They even searched for patterns that might encode mathematical constants like pi or prime numbers. The results were unambiguous. Nothing. No narrowband signals, no artificial patterns, no technological signatures of any kind. The radio emissions from 3I/ATLAS were purely natural. The electromagnetic noise of ionized gas and solar wind interactions. This null result is actually informative. If 3I/ATLAS were an artificial probe, even a dead one, we might expect some electromagnetic leakage. Electronics generate radio frequency interference. Power systems create electromagnetic fields. Even passive reflections of radar signals would look different from natural bodies. SETI researchers are trained skeptics who desperately want to find something real. This contradiction drives their methodical approach. They've investigated hundreds of candidate signals over the decades, tracking down each one to its source. Airport radar, microwave ovens, even microwave emissions from orbiting satellites have all created false alarms. Dr. Martinez emphasized an important point. If we detected a real artificial signal from 3I/ATLAS, we wouldn't hide it. We'd immediately alert the global community. The protocols require transparency. This would be the discovery of the millennium. No one would sit on that. The SETI post-detection protocols, developed through international consultation, outline exactly what would happen if a signal were confirmed. Alert the International Astronomical Union, request independent verification, inform government authorities, then release the information publicly. The days of potential cover-ups or secret knowledge are long past. The public fascination with hidden signals reveals something about human psychology. We want the universe to be populated with intelligence. We want to believe we're not alone. When an object like 3I/ATLAS appears with unusual properties, we project our hopes onto it. But SETI's silence regarding 3I/ATLAS speaks volumes. Their instruments, specifically designed to detect artificial transmissions, found only natural emissions. The silence was more telling than any signal could be. Every modern myth begins with a kernel of truth wrapped in layers of misunderstanding speculation, and wishful thinking. For 3, I/ATLAS, that kernel was its genuinely unusual chemistry and interstellar origin. From there, the internet did what the internet does best. It transformed scientific anomalies into evidence of alien intelligence. The transformation began innocently enough. On July 15, 2025, an amateur astronomer posted enhanced images of 3I/ATLAS to Reddit, noting the object's unusual trajectory and speed. Within hours, the post had thousands of upvotes and hundreds of comments speculating about artificial origins. Someone mentioned the carbon dioxide anomaly. Another noted the hydrogen line frequency. By evening, Twitter was ablaze with #AlienComet hashtags. The telephone game of scientific information in the digital age follows predictable patterns. A research paper states, unusual CO2 emissions detected. A science blog reports mysterious signals from interstellar object. A YouTube channel proclaims scientists baffled by alien transmissions. Each iteration adds drama while subtracting accuracy. Dr. Jennifer Walsh, who studies science communication at Stanford, tracked the rumor's evolution. Within 72 hours, careful scientific observations had morphed into claims of alien technology. The transformation was fascinating and depressing to watch in real time. Social media algorithms amplified the most engaging content, which meant the most sensational interpretations. Videos titled "NASA Hides Alien Signal" garnered millions of views, while actual astronomers explaining natural phenomena struggled to reach thousands. The attention economy rewards mystery over explanation, questions over answers. Think of how rumors spread in a small town, then multiply by global internet scale. Every person adds their interpretation, their hopes, their fears. The story evolves with each telling, shaped by what people want to believe rather than what evidence supports. The mainstream media played an inadvertent role. Headlines need to grab attention in a crowded information landscape. Interstellar Visitor shows unusual chemistry, doesn't drive clicks like "Scientists fear comet may be transmitting signals." Even when articles eventually explained the natural phenomena, readers often only absorbed the sensational headline. Influential science communicators tried damage control. They posted threads explaining radio astronomy, created videos about natural comet emissions, and patiently responded to questions. But debunking travels slower than rumors. Corrections rarely go viral. The myth gained institutional momentum when fringe websites began connecting dots that didn't connect. They linked 3I/ATLAS to previous interstellar visitors, creating narratives about alien surveillance or gradual contact. They cited legitimate scientists out of context, making careful speculation sound like confirmed belief. Dr. Carlos Rodriguez, whose paper on 3I/ATLAS's trajectory was widely misquoted, expressed frustration. "I wrote that the orbital path was remarkably convenient for observation. Somehow that became, scientist confirms alien probe positioned itself for Earth surveillance." The conspiracy ecosystem embraced 3I/ATLAS enthusiastically. YouTubers analyzed pixelated images for hidden structures. Podcasters interviewed experts with dubious credentials. Facebook groups formed around decoded messages from the visitors' supposed signals. Each community reinforced its own beliefs, creating echo chambers where speculation hardened into certainty. The psychological appeal is understandable. We live in uncertain times, and the idea of contact with advanced intelligence offers hope for solutions, or at least distraction from earthly problems. The myth of 3I/ATLAS as an alien transmitter provides meaning, mystery, and community for those who believe. But myths have consequences. Public understanding of astronomy suffers when fiction overwhelms fact. Research funding gets diverted to address public concerns rather than scientific priorities. Real discoveries get lost in noise about imaginary signals. The scientific community found itself fighting a two-front war, conducting legitimate research while simultaneously combating misinformation about that same research. But what if we're looking for the wrong kind of signal? What if our assumptions about alien communication are completely wrong? Radio emissions from comets sound like cosmic waterfalls when converted to audio, a constant rushing noise punctuated by pops and crackles. When astronomers first pointed radio telescopes at 3I/ATLAS, they heard exactly this: the natural song of ionized gas dancing with solar wind. But human brains evolved to find tigers in tall grass, insisted on finding patterns in the static. The process begins when solar ultraviolet radiation strikes molecules in the comet's coma. The energy strips electrons from atoms, creating a soup of charged particles. These ions spiral along magnetic field lines, emitting radio waves as they accelerate. It's physics, not communication, like the buzz of a neon sign rather than a broadcast signal. Dr. Alan Thompson at the National Radio Astronomy Observatory has spent decades listening to space. Natural radio emissions have a characteristic sound, he explains. They're broadband, chaotic, constantly changing. Artificial signals are narrow, stable, purposeful. The difference is like comparing wind in trees to a flute playing. When you analyze hours of cosmic static with modern software, interesting things happen. Fourier transforms reveal frequency components. Correlation algorithms find repeating patterns. Statistical analysis identifies outliers. The human tendency is to interpret these mathematical artifacts as meaningful, especially when the source is as unusual as 3I/ATLAS. Think of it like looking at clouds. Spend enough time and you'll see faces, animals, entire scenes. Your brain isn't finding real patterns. It's imposing familiar templates on random shapes. The same thing happens with radio data, except the patterns are mathematical rather than visual. The supposed signals from 3I/ATLAS followed predictable patterns of self-deception. Observers noted regularities in the static that seemed too perfect for nature, but these patterns appeared at different frequencies for different observers, never consistently, never repeatably. They were ghosts in the machine, artifacts of analysis rather than real phenomena. The extended carbon dioxide coma created particularly interesting radio emissions. As CO2 molecules broke apart under solar radiation, they created a complex symphony of electromagnetic noise. The scale, hundreds of thousands of kilometers, meant signals took measurable time to propagate across the cloud, creating echo effects that could seem artificial. Professional radio astronomers use techniques to separate real signals from noise. They observe the same object with multiple telescopes, looking for correlations. They observe at different times, checking for consistency. They use different analysis methods to ensure patterns aren't algorithmic artifacts. For 3I/ATLAS, every test pointed to natural origins. The emissions showed the characteristic randomness of thermal noise. The frequency distribution matched theoretical predictions for ionized gas. The temporal variations correlated with solar wind changes, not internal processes. Dr. Sarah Kim, who led the Green Bank Observatory's analysis, was blunt. We've analyzed petabytes of data. There's nothing artificial here. The emissions are textbook examples of natural plasma physics. They're interesting scientifically, but they're not signals. The hydrogen line detection near 1420 MHz created particular excitement because this frequency has special significance in SETI research. Hydrogen atoms naturally emit at this frequency when their electrons flip spin states. It's the most common element signaling at a frequency any technological civilization would recognize. But 3I/ATLAS wasn't transmitting at the hydrogen line. It was emitting broadband noise that happened to include this frequency. Like a waterfall that happens to include the note middle C in its roar, present but not purposeful. Some researchers tried more exotic analysis methods. They looked for prime number sequences in pulse timing. They searched for mathematical constants in frequency ratios. They even analyzed the data for signs of compression or encoding. Every search returned null results. The static told its own story, just not the one people wanted to hear. It spoke of an ancient object warming in our sun's light, releasing gases frozen for billions of years. The extended coma held another secret about how small objects could create such enormous phenomena. The carbon dioxide cloud surrounding 3I/ATLAS stretches 348,000 kilometers from its tiny nucleus, a volume so vast you could fit Earth's entire orbit around the Moon inside it. This isn't just large for a comet, it's impossibly large according to conventional models. Yet there it is, mapped in exquisite detail by the Spitzer Space Telescope, defying our understanding of how small objects create enormous phenomena. To grasp this scale, imagine a grain of sand creating a fog bank that covers an entire city. The physics seems wrong. How does a nucleus perhaps 5 kilometers across, smaller than Manhattan, maintain an active region larger than the distance between Earth and Moon? The energy requirements alone should be impossible. Dr. Patricia Anderson at the European Space Agency calculated the gas production rates. For 3I/ATLAS to sustain such an enormous coma, it would need to release about 100 kilograms of CO2 per second. That's reasonable for an active comet. But maintaining that rate across such a vast volume requires either extraordinary surface activity or distributed sources of gas. Natural processes can create large-scale phenomena, but they follow predictable patterns. Volcanic eruptions on Io create plumes hundreds of kilometers high. Saturn's moon Enceladus shoots geysers that feed an entire ring, but these are powered by tidal heating from massive planets. 3I/ATLAS has only the sun's distant warmth. The conventional explanation invokes fragmentation. Perhaps 3I/ATLAS isn't a single object, but a swarm of CO2-rich fragments flying in formation. Each piece contributes to the overall gas cloud, creating the illusion of a single enormous coma. Think of it like a flock of birds that looks like one large creature from a distance. This hypothesis makes testable predictions. Fragmented comets show brightness variations as different pieces rotate into view. They produce asymmetric comas as fragments outgas at different rates. High-resolution imaging should reveal multiple nuclei, or at least elongated structures suggesting recent breakup. But Hubble's images showed something different. The brightness remained remarkably stable. The coma appeared symmetric, centered on what looked like a single point source. If 3I/ATLAS was fragmenting, it was doing so in a way unlike any comet we've observed. Another possibility involves exotic ice physics. Laboratory experiments show that CO2 ice can behave strangely under conditions simulating interstellar space. Billions of years of cosmic ray bombardment can create amorphous structures that release gas explosively when heated. Perhaps 3I/ATLAS contains pockets of this processed ice, erupting as solar heating penetrates the surface. The extended cloud might also result from interaction with the solar wind. As charged particles from the sun strike the initial coma, they could accelerate CO2 molecules to high velocities, spreading them across a larger volume. This electromagnetic amplification could explain the size without requiring impossible gas production rates. Dr. Robert Chen proposed a radical idea. What if the measurement itself was wrong? Not the observation, Spitzer's data was solid, but our interpretation. Perhaps we're seeing CO2 from multiple sources along the line of sight, creating an illusion of a single enormous cloud. The timing of the extended coma discovery added to the mystery. When first detected in July, 3I/ATLAS showed a compact coma typical of comets at that distance. By August, it had expanded dramatically. The growth rate exceeded theoretical models by factors of 10. Size doesn't automatically mean artificial. Nature routinely creates structures that dwarf human comprehension. Jupiter's Great Red Spot could swallow Earth. The Bootes void spans 330 million light-years of nearly empty space. The observable universe itself is 93 billion light-years across. Scale alone doesn't indicate design. But the extended coma of 3I/A/TLAS pushes the boundaries of what we thought possible for cometary physics. It forces us to consider mechanisms we haven't seen before, processes that might be unique to interstellar objects or ancient ices. Then came the trajectory analysis that would add another layer to the mystery. The path 3I/ATLAS takes through our solar system reads like a cosmic choreography too perfect for coincidence. Starting from beyond Neptune's orbit, it plunges toward the Sun on a trajectory that threads between Earth and Mars, passes within observation range of our major planets, and exits through a gap in the asteroid belt. If you were designing a tour of the inner solar system, you couldn't plan it better. The mathematics are unambiguous. 3I/ATLAS follows a hyperbolic orbit with an eccentricity of 1.06, approaching perihelion on October 29, 2025, at 0.87 astronomical units from the Sun. Its closest approach to Earth, 1.88 astronomical units on December 12th. Close enough for detailed study, far enough to pose no threat. The geometry seems almost deliberately optimized. Dr. James Wilson at JPL ran Monte Carlo simulations of random interstellar trajectories. The probability of an object passing through our solar system with such favorable observation geometry, about 1 in 10,000. Rare, but not impossible given the vast number of interstellar objects that must exist. Think of it like this. If you threw a dart randomly at a map of the solar system, what are the odds it would land in the perfect spot for Earth-based observation? Low, but throw enough darts, or send enough interstellar objects, and eventually one hits the bullseye. The trajectory offers multiple observation opportunities that seem too convenient. On October 3rd, 3I/ATLAS passes within 0.19 astronomical units of Mars, allowing the Mars Reconnaissance Orbiter to capture high-resolution images. On March 6, 2026, it makes a distant approach to Jupiter, where the Juno spacecraft might attempt observations. These alignments aren't impossible. Orbital mechanics allows for complex trajectories. But the cumulative effect creates an illusion of purpose. Our pattern-seeking brains interpret the trajectory as evidence of navigation rather than chance. The approach angle adds another curious detail. 3I/ATLAS enters the solar system from the direction of the constellation Lyra, roughly perpendicular to the ecliptic plane where planets orbit. This high-inclination approach provides excellent viewing geometry from Earth while minimizing gravitational perturbations from planets. Professional astronomers understand that cosmic coincidences happen regularly. The universe is vast enough that million-to-one chances occur somewhere every day. Earth itself exists in a Goldilocks zone that seems perfectly tuned for life, not because it was designed, but because we wouldn't be here to observe it otherwise. The anthropic principle applies here. We notice 3I/ATLAS precisely because its trajectory allows us to observe it. Thousands of interstellar objects might pass through the outer solar system undetected. We only see the ones with favorable geometry, creating a selection bias that makes perfect trajectories seem common. Dr. Lisa Martinez calculated the gravitational influences on 3I/ATLAS throughout its passage. Every planet, every major asteroid, even the Sun's radiation pressure creates tiny perturbations. Yet the trajectory remains remarkably stable, suggesting a dense, cohesive object rather than a loose aggregate. The timing seems theatrical. 3I/ATLAS arrives just as our detection capabilities reach the necessary sensitivity. It becomes active just as our spectroscopic instruments can analyze its composition. It passes through our solar system just as humanity develops the technology to study it properly. But step back, and the coincidence dissolves. Interstellar objects have been passing through our solar system for billions of years. We're only now capable of detecting them. The coincidence isn't that 3I/ATLAS arrived now, it's that we finally have the tools to see it. The trajectory analysis revealed one genuinely puzzling aspect. 3I/ATLAS shows no measurable non-gravitational acceleration. Unlike Oumuamua, which mysteriously sped up as it left the solar system, 3I/ATLAS follows pure gravitational dynamics. Its path is predictable, mathematical, almost boringly normal, except for its incredible speed. October 29th would change everything, or would it? As 3I/ATLAS approached perihelion, it would disappear behind the Sun, hidden from Earth's view at the moment of maximum activity. October 29th, 2025, marks the climax of 3I/ATLAS's solar performance, its closest approach to our star at 130 million kilometers. Solar heating peaks, ice sublimation reaches maximum, and any dramatic changes in behavior should occur. But Earth sits on the wrong side of the Sun, blind to the show. For 2 months, from late September through November, our interstellar visitor performs unseen, hidden in our star's glare. The cosmic timing feels almost cruel. Imagine preparing for months to photograph a rare eclipse, only to have clouds appear at the crucial moment. Except these clouds are 1.4 million kilometers of nuclear fusion that no telescope can penetrate. We get the build-up and aftermath, but miss the main event entirely. Dr. Amanda Foster at NASA calls it the most frustrating conjunction in modern astronomy. All of Earth's most powerful instruments, Hubble, James Webb, the combined radio telescopes of 6 continents, become useless for observing 3I/ATLAS, precisely when the object should be most active and revealing. Think of perihelion like a chemical reaction's activation energy. As 3I/ATLAS approaches the Sun, increasing heat penetrates deeper into its nucleus. Ices that remained frozen for billions of years suddenly sublimate. If the object has layered structures, they might separate. If it contains volatile pockets, they could explode, all invisible to Earth's eager eyes. The blackout isn't just an inconvenience, it's a fundamental limitation of inner solar system observations. When objects pass between Earth and the Sun, they enter a zone where solar radiation overwhelms any signal they produce. It's like trying to see a firefly while staring at a searchlight. The Mars opportunity offers partial compensation. On October 3rd, while Earth remains blind, Mars Reconnaissance Orbiter gets a front-row seat as 3I/ATLAS passes within 29 million kilometers. MRO's high-rise camera, designed to photograph the Martian surface, could theoretically capture images of the visitor at about 30 meters per pixel resolution. But MRO wasn't designed for comet observation. Tracking a fast-moving object requires precise timing and orbital adjustments that push the spacecraft's capabilities. The images, if successful, would show only basic morphology, not the detailed spectroscopy Earth-based instruments could provide. Some researchers proposed creative solutions. Could we use solar observatories like SOHO or the Parker Solar Probe to monitor 3I/ATLAS during conjunction? These spacecraft are designed to study the Sun with instruments specifically built to handle intense radiation, but their fields of view and sensitivities aren't optimized for comet observation. The European Space Agency's Solar Orbiter, launched in 2020, orbits between Mercury and Earth. Its position during October 2025 might allow oblique observations of 3I/ATLAS. But again, instruments designed for solar physics aren't ideal for studying interstellar visitors. The timing conspiracy extends beyond simple geometry. As 3I/ATLAS disappears from view, it enters the phase where CO2 ice sublimation should peak. The mysterious extended coma might dramatically expand or collapse. The chemistry might shift from CO2 dominance to revealing hidden water reserves. The nucleus might fragment or remain stable. We can only guess. historical precedent offers little comfort. Comet Ison in 2013 approached the Sun with great fanfare, only to disintegrate during perihelion, an event partially hidden from Earth's view. We learned of its destruction only through indirect observations and spacecraft glimpses. 3. I/ATLAS could undergo similar dramatic changes while we watch helplessly. Dr. Chen calculated what we're missing. During the 2-month blackout, 3 I/ATLAS travels nearly 500 million kilometers, experiences temperature variations of over 200 degrees Celsius, and potentially releases more gas than during the entire rest of its solar system passage. It's like missing the middle act of a 3-act play. The December reappearance will show us 3 I/ATLAS transformed by its solar encounter, but we'll have to reverse engineer what happened during conjunction from the aftermath. Like detectives arriving at a scene hours after the crime, we'll piece together events from whatever evidence remains, but other eyes were watching from angles Earth couldn't achieve. Humans are meaning-making machines, hardwired to find patterns, purpose, and communication, even in randomness. When 3 I/ATLAS arrived with its unusual properties, our collective psychology projected onto it every hope and fear about cosmic loneliness. The signals people claimed to detect revealed more about human nature than alien intelligence. The phenomenon isn't new. In 1877, astronomer Giovanni Schiaparelli observed canali on Mars, channels that English speakers translated as canals, implying artificial construction. Percival Lowell built an entire Martian civilization from these optical illusions, complete with a dying race desperately irrigating their desert world. The canals existed only in the imperfect lenses and hopeful imagination of observers. Dr. Susan Richards, a cognitive psychologist studying scientific interpretation, explains, "We don't see the world as it is. We see it as we are. When we desperately want the universe to contain intelligence, we interpret ambiguous data as evidence of that intelligence." The WOW signal of 1977 exemplifies this tendency. For 72 seconds, the Big Ear Radio Observatory detected something extraordinary, a narrowband transmission of incredible strength at precisely the hydrogen line frequency. Astronomer Jerry Amon wrote "wow" in the margins, and decades of mythology followed. Despite exhaustive searches, the signal never repeated. Natural explanations exist, but the mystery persists, because we want it to be aliens. Think of it like seeing faces in clouds, or hearing voices in white noise. The technical term is pareidolia, the tendency to interpret vague stimuli as familiar patterns. For 3 I/ATLAS, pareidolia operated on multiple levels: visual, seeing structures in pixelated images; auditory, hearing patterns in radiostatic; and mathematical, finding significance in random number sequences. The psychological need for cosmic companionship runs deep. We evolved as social creatures in a universe that seems utterly indifferent to our existence. The possibility that 3 I/ATLAS might be artificial offers relief from existential loneliness. We're not alone. Someone else survived the Great Filter. Intelligence is possible elsewhere. Social media amplified these psychological tendencies exponentially. Every amateur astronomer who thought they saw something unusual could instantly share it with millions. Confirmation bias operated at network scale. People who wanted to believe found each other, reinforcing interpretations that mainstream science rejected. The conspiracy mindset added another layer. If 3 I/ATLAS was transmitting and governments knew, wouldn't they hide it? The absence of official confirmation became evidence of cover-up. The more scientists explained natural phenomena, the more suspicious some people became. Dr. Richards studied online communities devoted to 3 I/ATLAS signals. She found remarkable consistency in how people interpreted random data. They saw prime numbers, mathematical constants, even attempted messages. The patterns weren't in the data. They were templates in human cognition projected onto noise. History provides sobering examples. In 1967, Jocelyn Bell Burnell detected incredibly regular radio pulses from space. The signal was so artificial seeming that the Discovery team privately called it LGM-1 for Little Green Men. They even considered the ethical implications of announcing contact with alien intelligence. Then they found another pulsar, and another. The aliens were rotating neutron stars. Fast radio bursts followed a similar trajectory. First detected in 2007, these millisecond chirps of radio energy seemed too structured to be natural. Theories ranged from alien propulsion systems to communication beacons. Years of research revealed them as natural phenomena, magnetars, neutron star collisions, exotic but not artificial. The 3I/ATLAS signal claims followed predictable patterns. Initial excitement. Scientists detect patterns. Followed by speculation. Could this be first contact? Then clarification. Astronomers explain natural origins. And finally entrenchment. They're hiding the truth. Each cycle reinforced beliefs rather than updating them with new evidence. The tragedy is that the real 3I/ATLAS is fascinating enough without fictional signals. An interstellar visitor with bizarre chemistry, an extended coma that challenges physics, a journey of billions of years. These truths are more wondrous than the myths. The real mystery was even stranger than imagined signals. Science has developed precise criteria for distinguishing artificial phenomena from natural ones, refined through decades of false alarms and careful analysis. When applied to 3I/ATLAS, these tests paint a clear picture. Unusual, yes. Artificial, no. But understanding why requires examining what would actually indicate non-natural origins. The fundamental principle is simple. Artificial objects do things nature cannot. They concentrate energy in narrow frequency bands. They maintain structures that require active control. They show mathematical regularities that don't arise from physical laws. They contain materials or isotope ratios that require technological processing. Dr. Michael Torres, who leads SETI's signal verification team, outlines the hierarchy of evidence. First, we look for signals that violate thermodynamics, narrowband transmissions that nature can't produce. Second, we check for information content, modulation patterns that carry data. Third, we verify repeatability. Can multiple observers detect the same phenomenon? For 3I/ATLAS, every test returns negative. The radio emissions are broadband thermal noise, exactly what ionized gas produces. No modulation patterns encode information. The signals appear different to each observer because they're detecting random noise, not structured transmissions. Think of it like distinguishing between a forest fire and a smoke signal. Both produce smoke, but one carries intentional patterns while the other spreads chaotically. 3I/ATLAS produces the electromagnetic equivalent of wildfire smoke, dramatic but meaningless. The structural evidence also points to natural origins. While 3I/ATLAS's chemistry is unusual, it falls within the range of possible natural compositions. The extended CO2 coma, while surprising, can be explained through exotic but physical processes. The trajectory, while convenient, follows pure gravitational dynamics without the corrections that would indicate propulsion. Artificial objects should show certain technological signatures. Refined metals or synthetic materials would appear in spectroscopy. Geometric structures would create distinctive radar returns. Active systems would produce waste heat visible in infrared. Communication equipment would leak electromagnetic radiation at characteristic frequencies. 3I/ATLAS shows none of these indicators. Its spectrum reveals only common molecules: water, carbon dioxide, simple organics. Its radar signature matches a rough, irregular surface. Its thermal emission follows blackbody radiation laws. Any radio frequency leakage is absent or below detection thresholds. The burden of proof for extraordinary claims requires extraordinary evidence. Carl Sagan popularized this principle, but it reflects centuries of scientific methodology. The more a claim contradicts established knowledge, the stronger the evidence must be to support it. Claiming 3I/ATLAS is artificial contradicts enormous amounts of established science. It requires either a conspiracy of global proportions or fundamental errors in our understanding of physics. Neither is impossible, but both demand evidence far stronger than unusual chemistry and coincidental timing. Dr. Jennifer Park at MIT applied Bayesian analysis to the artificial hypothesis, starting with prior probabilities based on the lack of confirmed alien detection. She updated these with each observation. The unusual chemistry slightly increased artificial probability. The extended coma added minor weight. But the natural radio emissions and normal dynamics pushed probability back towards zero. The final calculation, less than 0.001% chance of artificial origin based on current evidence. Not impossible, but so unlikely that natural explanations, however exotic, remain preferable. Historical examples reinforce this conclusion. Every past claim of artificial signals or objects has eventually yielded to natural explanation. Pulsars weren't alien beacons. Fast radio bursts weren't propulsion systems. Oumuamua's acceleration came from outgassing, not light sails. The pattern is consistent. Nature is stranger than we imagine, but not artificial. Some argue this history creates bias against recognizing real artificial phenomena. Perhaps we're so conditioned to finding natural explanations that we'd miss actual alien technology. This concern has merit, but doesn't change the evidence. 3I/ATLAS fails every test for artificiality we know how to apply. Unless we're using the wrong tests, looking for the wrong signatures, making the wrong assumptions about what alien technology would look like. Let's step into purely speculative territory, clearly marked and carefully reasoned. If 3I/ATLAS were transmitting intentional signals, which all evidence suggests it is not, what would that actually look like? This thought experiment reveals why scientists are so confident in natural explanations. First, consider the engineering challenge. An artificial probe traveling for millions of years would need power sources that could survive cosmic radiation, micrometeorite impacts, and extreme temperature cycles. Radio transmitters require stable oscillators, amplifiers, and antennas. After billions of years in interstellar space, maintaining functional electronics would represent technology beyond human comprehension. Dr. Robert Anderson, who designs deep space communication systems, explains the reality. Our most robust spacecraft last decades, maybe centuries if we're optimistic. Voyager's still transmitting after 47 years, but barely. Something operating for millions of years. That's magic, not engineering. If 3I/ATLAS were broadcasting, the signals would show unmistakable characteristics. Narrow bandwidth, probably under 1 Hz wide, stable frequency, maintained by atomic clocks or quantum references. Doppler shift exactly matching the object's motion. Information content encoded through amplitude, frequency, or phase modulation. Think of how human spacecraft communicate. New Horizons, billions of kilometers away, transmit signals so precise we can detect them despite being weaker than a cell phone's emission. The signals are narrow, stable, and carry digital data. Natural phenomena simply cannot mimic these characteristics. The power requirements pose another challenge. To transmit detectable signals across interstellar distances requires either enormous power or exquisite focusing. A omnidirectional beacon would need gigawatts, impossible for something 3I/ATLAS's size. A directed beam would need to know where to aim, implying active tracking of potential receivers. Let's imagine advanced aliens solve these problems. Their probe uses exotic power sources, antimatter, micro black holes, or technologies we can't conceive. It maintains quantum coherence despite billions of years of decoherence. It actively tracks technological civilizations and adjusts transmission accordingly. Even granting these miraculous capabilities, the signals would still be detectable. SETI searches cover vast frequency ranges with sensitivities that could detect airport radar from nearby stars. The Allen Telescope Array monitors millions of channels simultaneously. The absence of detection isn't from lack of trying, it's from lack of signals. Some propose we might miss alien transmissions because they use communication methods we don't understand. Perhaps they modulate gravitational waves, manipulate quantum entanglement, or use dimensions we can't perceive. While creative, these ideas violate known physics, or require capabilities that would leave other detectable traces. The decoding challenge offers another thought experiment. Suppose 3I/ATLAS transmitted signals so alien we couldn't recognize them as artificial. The signals would still show statistical properties different from noise. Information theory provides mathematical tools for detecting structure, regardless of encoding method. Dr. Lisa Chen applied these tools to 3I/ATLAS's emissions. She searched for entropy variations that would indicate information content. She looked for compression signatures suggesting efficient encoding. She analyzed correlation functions that would reveal hidden patterns. Every test returned results consistent with random thermal noise. The trajectory argument, that 3I/ATLAS's path seems too convenient, doesn't support broadcasting either. If aliens wanted to communicate, why send a probe on a hyperbolic trajectory that spends only months in our solar system? Why not park it at a Lagrange point for extended observation? Why hide transmissions in natural-seeming emissions? Cultural assumptions might blind us to alien communication methods. Perhaps they consider radio primitive, like smoke signals to us. But physics constrains possibilities. Electromagnetic radiation remains the fastest, most efficient way to transmit information across space. Any technological civilization would understand this. The null hypothesis, that 3I/ATLAS is entirely natural, explains all observations without requiring spectacular assumptions. Occam's razor isn't just philosophical preference, it's practical methodology that prevents us from building elaborate fantasies on insufficient evidence. But broadcasting might not be the right word for what 3I/ATLAS represents. Perhaps the message isn't in electromagnetic signals, but in the object itself. The cosmos is filled with natural radio transmitters, far more powerful and strange than any human technology. From pulsars spinning hundreds of times per second to masers amplifying molecular emissions, nature creates beacons that would seem impossibly artificial if we didn't understand the physics. 3I/ATLAS joins this cosmic chorus as another natural transmitter, remarkable but not artificial. Jupiter broadcasts radio storms that would deafen any receiver within millions of kilometers. These emissions arise from charged particles spiraling through the planet's magnetic field, accelerating electrons that generate synchronized radiation. The signals are so strong that amateur radio operators on Earth can detect them with backyard antennas. Yet no one claims Jupiter is artificial. Dr. Patricia Williams studies astrophysical mesas, regions where molecules amplify radio emissions like cosmic lasers. In star-forming regions, water and methanol molecules create natural mesas millions of times more powerful than anything humans have built. They produce narrowband signals that would seem absolutely artificial if we didn't understand the quantum mechanics. Think of cosmic mesas as nature's broadcast towers. When specific conditions align, the right temperature, density, and radiation field, molecules enter excited states that cascade together, producing coherent radiation. The process is entirely natural, but creates signals that early SETI researchers had to carefully distinguish from potential alien transmissions. Pulsars remain the gold standard for natural phenomena that seem artificial. These city-sized neutron stars spin with periods measured in milliseconds, sweeping lighthouse beams of radiation across space. The first detected pulsar, CP1919, produced pulses so regular that discoverers briefly considered alien origin. Now we know thousands of pulsars, each a natural transmitter of extraordinary precision. Fast radio bursts represent nature's latest surprise. These millisecond flashes release as much energy as the sun produces in days. When first detected, their properties seemed impossible. Too bright, too brief, too structured. Theories ranged from alien propulsion to communication beacons. Years of research revealed magnetars as the likely source, neutron stars with magnetic fields so strong they can crack their own crusts, releasing enormous energy bursts. 3I/ATLAS's emissions fit perfectly within this context of natural transmitters. The ionized gas in its coma acts like a weak plasma screen, scattering and modulating solar wind particles. The process creates broadband radio noise, cosmic static indistinguishable from countless other natural sources. The hydrogen line frequency that excited observers is ubiquitous in space. Hydrogen, the universe's most abundant element, naturally emits at 1420 MHz when electrons flip spin states. Every gas cloud, every stellar atmosphere, every comet with hydrogen compounds produces this emission. Finding it from 3I/ATLAS is like finding water in the ocean, expected, not extraordinary. Dr. James Rodriguez explains the selection bias. We look for alien signals at the hydrogen line because it's universal. But that also means natural hydrogen emission is everywhere. It's the worst possible frequency for distinguishing artificial from natural sources. The extended CO2 coma creates its own transmission effects. As molecules break apart under solar radiation, they produce a cascade of emissions across the electromagnetic spectrum. The scale, hundreds of thousands of kilometers, means these emissions overlap and interfere, creating complex patterns that can seem structured but are actually chaotic. Natural transmission mechanisms in 3I/ATLAS likely include thermal emission from heated dust, synchrotron radiation from charged particles in magnetic fields, and molecular line emissions from various chemical species. Each process contributes to the overall radio signature, creating a complex but entirely natural symphony. Some comets produce X-ray emissions through charge exchange between solar wind ions and cometary neutrals. Others generate ultraviolet auroras as particles impact their atmospheres. These high-energy emissions would seem exotic if we didn't understand the underlying physics. The chemistry told a different story about 3I/ATLAS's nature, not through transmissions, but through molecular signatures from another star system. If 3I/ATLAS carries any message, it's written in chemistry, not radio waves. The bizarre carbon dioxide dominance, the suppressed water signature, the extended coma, these features encode information about stellar environments we've never visited, planetary formation conditions we've only theorized, and chemical processes operating billions of years ago in regions of space we'll never reach. The 8:1 carbon dioxide to water ratio tells a story of formation in an alien chemical environment. In our solar system, water dominates because oxygen is more abundant than carbon, and hydrogen is the most common element. But around carbon-rich stars, or in regions with different element ratios, CO2 might naturally dominate. Dr. Michelle Park, an astrochemist studying protoplanetary discomposition, explains, every stellar system has a chemical fingerprint determined by the star's composition and the disk's thermal structure. 3I/ATLAS's chemistry suggests formation around a star with unusual carbon-to-oxygen ratios, possibly a carbon star or an evolved giant. Think of it like geological layers encoding Earth's history. Each stratum tells of ancient climates, catastrophes, and evolution. Similarly, 3I/ATLAS's ice layers preserve the chemical conditions of its birthplace, frozen in time for billions of years until our sun's heat released them for spectroscopic reading. The thick disk origin hypothesis adds temporal depth to this chemical message. If 3I/ATLAS formed 8 to 12 billion years ago, it samples the galaxy's chemistry from an earlier epoch. The universe contained fewer heavy elements then, formed by fewer generations of supernovae. The unusual composition might reflect not just different stellar environments, but different cosmic chemistry entirely. Isotope ratios, if we could measure them precisely, would provide even more specific information. Different stellar processes produce different isotopic signatures. Supernovae create neutron-rich isotopes. Asymptotic giant branch stars produce specific carbon isotopes. Each stellar type leaves distinctive isotopic fingerprints in the material it produces. The extended coma phenomenon might encode information about radiation processing during interstellar travel. Billions of years of cosmic ray bombardment can transform ice structure, creating amorphous phases that release gas differently than pristine ice. The enormous CO2 cloud might result from explosive sublimation of radiation-processed material. Dr. Robert Thompson models interstellar chemistry. Cosmic rays can break molecular bonds and create radicals that recombine in unusual ways. After billions of years, you get chemistry that can't exist in protected planetary environments. 3I/ATLAS might carry exotic molecules we've never seen. The visitor serves as a messenger between stellar generations. Stars that contributed material to 3I/ATLAS might have died billions of years ago, their planetary systems long dispersed. Yet their chemical signatures persist in this wandering fragment, carrying information across space and time, like a message in a bottle crossing an ocean. 3 visitors, Oumuamua, Borisov, 3I/ATLAS, have shown 3 distinct chemical personalities. Oumuamua appeared dry, showing no obvious volatiles. Borisov displayed carbon monoxide enhancement. 3I/ATLAS exhibits CO2 dominance. This diversity suggests the galaxy contains a vast library of chemical environments, each producing distinctive planetary materials. The implications for astrobiology are profound. If chemistry varies this dramatically between stellar systems, then the building blocks of life might assemble differently elsewhere. Carbon-rich environments might favor different organic chemistry. Water-poor conditions might drive alternative biochemistry. Life, if it exists, might use chemical strategies we haven't imagined. The December observations will test whether 3I/ATLAS's chemistry changes after perihelion. If water vapor appears as the object cools, it would suggest thermal suppression rather than true water depletion. If CO2 dominance persists, it implies fundamental compositional differences that no amount of heating can alter. But the chemical message extends beyond composition to include dynamics, the way gases escape, how dust particles organize, the interaction between solar radiation and cometary material, all encode information about physical processes in alien environments. 3 visitors, 3 chemical signatures, 3 glimpses of the galaxy's true diversity. 3I/ATLAS adds another data point to the most profound question in astronomy. If the universe should be teeming with life, where is everybody? The Fermi paradox, the contradiction between high probability of alien civilizations and complete lack of evidence for them, gains new complexity with each interstellar visitor that proves entirely natural. Enrico Fermi's famous lunchtime question in 1950 sparked decades of calculation and speculation. The Drake equation suggests millions of technological civilizations should exist in our galaxy. Yet we see no megastructures, detect no signals, find no probes. 3I/ATLAS could have been evidence of alien technology, but instead reinforces the Great Silence. Dr. Jennifer Martinez, who studies astrobiology at Cornell, frames the issue precisely. Every natural interstellar object we discover makes the absence of artificial ones more statistically significant. If aliens were sending probes, we should have found one by now. the fact that we haven't tells us something important. The numbers are sobering. If even one civilization achieved interstellar capability millions of years ago, they could have explored the entire galaxy by now. Self-replicating probes could visit every star system in under 10 million years, a cosmic eye blink. Yet 3I/ATLAS shows no signs of technology, no evidence of purpose, no indication of intelligence. Think of it this way. We've been broadcasting radio signals for over a century, creating an expanding bubble of electromagnetic evidence of our existence. Any civilization within 100 light-years could detect us with technology no better than our own. If they responded with probes traveling at even 1% light speed, we should be seeing arrivals now. Instead, we get natural comets. The Great Filter hypothesis suggests something prevents life from spreading across the galaxy. Perhaps life itself is extraordinarily rare. Perhaps intelligence rarely evolves. Perhaps technological civilizations inevitably destroy themselves. Or perhaps the jump to interstellar travel is essentially impossible. 3I/ATLAS's natural origin supports any of these possibilities. Some argue that absence of evidence isn't evidence of absence. Space is vast, our search is limited, our assumptions potentially wrong. Perhaps aliens communicate through methods we can't detect. Perhaps they deliberately hide from primitive civilizations. Perhaps they're already here but unrecognized. These possibilities remain, but each natural interstellar visitor makes them less likely. The zoo hypothesis suggests advanced civilizations might deliberately avoid contact, observing us like animals in a preserve. But 3I/ATLAS shows no signs of observation equipment, no indication of being anything other than ancient ice and rock following gravitational laws. Dr. Carlos Wang applies statistical analysis. If intelligent probes were as common as natural interstellar objects, we'd have a 50% chance of detecting one by now. If they're 10 times rarer, the probability drops to 5%. The non-detection is becoming statistically meaningful. The sociological implications trouble many researchers. Humanity has spent centuries imagining we're not alone, building mythologies around visitors from the stars. The possibility that we might be truly isolated in an empty galaxy challenges fundamental assumptions about our cosmic significance. Yet 3I/ATLAS also offers hope. It proves material can travel between star systems, carrying chemistry and perhaps biology across interstellar distances. Panspermia, the hypothesis that life spreads naturally between worlds, remains viable even if intelligent signals don't exist. The timing argument cuts both ways. Earth has only been obviously biological for about 2 billion years, technological for mere centuries. In a galaxy 10 billion years old, we're newcomers. Perhaps we're among the first technological civilizations, not late to a crowded party, but early to an empty one. The observation selection effect matters too. We can only detect interstellar visitors that pass close enough and bright enough for our instruments. Thousands might transit the outer solar system unnoticed. The true population could be enormous, potentially including artificial objects we simply haven't detected yet. December's reappearance would be crucial for testing whether 3I/ATLAS showed any delayed signs of artificial origin. Let's clearly mark this as speculation while exploring a troubling possibility. What if 3I/ATLAS is artificial, but uses technology so advanced we can't recognize it? This thought experiment reveals both the limits of our detection methods and why scientists remain confident in natural explanations. Advanced civilizations might communicate through gravitational waves, manipulating space-time itself to send messages. The LIGO and Virgo detectors can sense ripples from colliding black holes billions of light-years away, but they're tuned for massive events, not subtle modulations that might carry information. If 3I/ATLAS generated gravitational signals, we'd never know. Dr. Alan Peterson, a theoretical physicist studying exotic communication methods, explains, a civilization million years ahead of us might consider radio as primitive as smoke signals. They could use quantum entanglement, manipulate dark matter, or employ physics we haven't discovered. Our instruments would be blind to such technologies. Think about how recently we've discovered fundamental aspects of reality. Dark energy, comprising 68% of the universe, was unknown until 1998. Dark matter, 27% of everything, remains mysterious. We understand only 5% of the cosmos. Alien technology might operate in that vast unknown, invisible to instruments designed for the narrow slice we comprehend. Quantum communication offers intriguing possibilities. While quantum entanglement can't transmit information faster than light, a common misconception, it could enable unhackable encrypted channels. If 3I/ATLAS communicated through quantum channels with some distant civilization, no classical instrument could detect the exchange. Metamaterials might render objects invisible to certain observations. We've created materials that bend light around objects, achieving limited invisibility. Advanced aliens might engineer materials that appear natural to our instruments while hiding artificial structures. 3I/ATLAS's unusual spectroscopy could theoretically result from engineered surfaces mimicking natural compositions. The biotechnology convergence suggests another detection challenge. Sufficiently advanced technology might be indistinguishable from biology. If 3I/ATLAS were a living spacecraft, grown rather than built, it might lack the metal signatures and geometric structures we associate with technology. Its chemistry could be both artificial and organic. Nanotechnology poses similar detection problems. A probe composed of billions of microscopic robots might appear as ordinary dust and gas. The extended CO2 coma could theoretically consist of nanomachines too small for optical telescopes to resolve, performing functions we can't imagine while appearing entirely natural. Dr. Susan Chen raises an unsettling point. We look for technology based on our own development path: radio, metals, geometric structures. But that's like expecting all life to be DNA-based, because Earth life is. Alien technology might follow completely different principles. Timescales matter too. If 3I/ATLAS is billions of years old, any technology might have degraded beyond recognition. Self-repair systems might have failed. Power sources might have depleted. What we observe could be a defunct probe, its artificial nature erased by cosmic erosion. But here's why scientists reject these speculations. They're unfalsifiable. Science progresses through testable hypotheses. Claiming undetectable technology is like claiming invisible unicorns. Impossible to disprove, but useless for understanding reality. We must work with what we can measure, not what we can imagine. The absence of recognizable technology in 3I/ATLAS doesn't prove it's natural, just as absence of dragons doesn't prove they don't exist. But in practice, we must operate on probabilities. Every test we can perform indicates natural origin. Speculating about undetectable technology might be philosophically interesting, but scientifically sterile. Dr. Martinez summarizes the scientific position. Could 3I/ATLAS be artificial in ways we can't detect? Yes. Could it also be a cosmic teapot or flying spaghetti monster in ways we can't detect? Also, yes. That's why we focus on what we can measure. But why it probably is in this case comes down to convergent evidence. Multiple independent observations using different techniques all point to natural origin. The real fear wasn't about signals or technology, but something more fundamental to scientific inquiry. The real terror keeping astronomers awake isn't alien invasion or secret signals from 3I/ATLAS. It's far more mundane and heartbreaking. The closing observation window and the data that will be forever lost when this unique visitor disappears into interstellar darkness, taking its secrets beyond recovery. Dr. Rachel Thompson at the European Southern Observatory expresses the genuine anxiety. We have maybe 6 months to study an object that won't return for infinity. Every cloudy night, every technical delay, every hour of lost telescope time means questions that will never be answered. That's what keeps me up at night. Think of it like having a few minutes to examine the only copy of an ancient manuscript before it crumbles to dust. You can't photograph every page, translate every word, or understand every symbol. You must choose what to preserve, knowing that everything else vanishes forever. That's the situation with 3I/ATLAS. The December reappearance after solar conjunction offers perhaps 12 weeks of good observation before 3I/ATLAS fades below detection limits. In that time, astronomers must gather enough data to spend years analyzing, knowing they can never go back for clarification or confirmation. The technical challenges compound the urgency. As 3I/ATLAS recedes, signal-to-noise ratios plummet. Spectroscopy that takes hours in December will take days in January, weeks in February. By March, even the most powerful telescopes will struggle to detect anything beyond position and brightness. Every measurement involves trade-offs. Time spent on high-resolution imaging means less time for spectroscopy. Radio monitoring prevents optical observation. Each telescope pointed at 3I/ATLAS can't observe other targets. The entire astronomical community must balance competing priorities with irreversible consequences. Dr. James Wilson coordinates observations for the International Astronomical Union. We're essentially performing triage. Which observations are most critical? What can we delay? What must we sacrifice? These decisions will affect our understanding for decades. The peer review process, normally measured in months, has compressed to days. Papers about 3I/ATLAS appear on preprint servers within hours of observations. The usual careful verification gets shortcuts as researchers race against the cosmic clock. Funding represents another fear. Telescope time costs thousands of dollars per hour. Emergency observations disrupt carefully planned research programs. Someone's years-long project gets delayed so we can study 3I/ATLAS. The political and financial pressures are enormous. Graduate students face particular challenges. A PhD thesis on 3I/ATLAS must be largely complete before the object disappears. There's no possibility of follow-up observations, no chance to fill gaps in data. Entire careers depend on measurements that must be perfect the first time. The historical precedent haunts everyone. Comet Ison in 2013 was supposed to be the comet of the century, but disintegrated at perihelion. Years of preparation yielded limited science. 3I/ATLAS could fragment, fade unexpectedly, or behave in ways that invalidate observation plans. Data preservation becomes critical. Every photon collected from 3I/ATLAS must be archived, catalogued, and preserved for future analysis. Storage systems that might seem adequate could prove insufficient as researchers discover new analysis techniques years from now. Dr. Chen articulates a deeper fear. What if the key to understanding interstellar objects is something we're not measuring? What if future instruments could answer questions we don't know to ask? We're like 19th century astronomers looking at stars, not knowing about nuclear fusion. The international coordination, while impressive, remains imperfect. Language barriers, time zones, and cultural differences create communication challenges. Critical observations might be missed simply because the right people didn't talk at the right time. Competition versus collaboration creates tension. Every research group wants priority on discoveries, but sharing data is essential for comprehensive understanding. The balance between openness and advantage shifts daily. Because the truth is more wonderful than any fiction we could imagine about alien signals, Strip away the speculation about alien signals and 3I/ATLAS reveals itself as something genuinely extraordinary. A natural time capsule from another star system, carrying chemical signatures from the galaxy's youth, demonstrating physics we've only theorized, and expanding our understanding of planetary formation across the cosmos. The confirmed facts alone astound. Here's an object moving at 209,000 kilometers per hour, so fast it could orbit Earth in under 12 minutes. It's been traveling for potentially 8 billion years, longer than our solar system has existed. Its chemistry inverts everything we thought we knew about cometary composition. These aren't mysteries requiring alien explanation. They're natural wonders exceeding fiction. Dr. Patricia Anderson catalogues what we've actually learned. 3I/ATLAS has taught us that carbon dioxide can dominate cometary chemistry, that small objects can maintain enormous gas clouds, that interstellar objects can remain active after billions of years in deep space. Each discovery reshapes planetary science. The extended CO2 coma remains genuinely puzzling without invoking artificial origins. Spanning 348,000 kilometers from a nucleus perhaps 5 kilometers across, it demonstrates that small bodies can influence vast volumes through processes we're still deciphering. Whether through fragmentation, explosive sublimation, or exotic ice physics, nature creates phenomena that dwarf human engineering. Think about what this visitor represents. Actual material from another star's protoplanetary disk delivered to our doorstep for analysis. We're conducting chemistry experiments on samples from light years away, studying formation conditions in alien stellar environments, touching matter that condensed when the universe was half its current age. The trajectory, while convenient for observation, follows beautiful mathematical curves predicted by Newton and Einstein. No mysterious accelerations like Oumuamua, no violations of physics, just pure gravitational dynamics playing out across cosmic scales. The precision of orbital mechanics allows us to predict 3I/ATLAS's position centuries into the future. The chemical diversity revealed by 3 interstellar visitors suggests the galaxy harbors an enormous variety of planetary environments: water-dominated comets like Borisov, dry objects like Oumuamua, CO2-rich bodies like 3I/ATLAS. Each samples different formation conditions, temperatures, and chemical processes. Dr. Michael Roberts studies implications for astrobiology. If chemistry varies this much between stellar systems, life might arise through pathways we haven't imagined. 3I/ATLAS shows us that Earth-like conditions might be just one option among countless possibilities. The preservation of volatile ices after billions of years demonstrates remarkable chemical stability. Despite cosmic radiation, micrometeorite impacts, and passage near unknown numbers of stars, 3I/ATLAS retained enough CO2 to create its enormous coma. This longevity suggests interstellar space might preserve complex molecules, possibly including organic precursors to life. The thick disk origin connects 3I/ATLAS to the galaxy's evolution. This visitor formed when different stellar populations dominated, when heavy elements were rarer, when the galaxy itself was more chaotic. We're studying not just another planetary system, but another epoch of cosmic history. Technological advances driven by 3I/ATLAS observations benefit all astronomy. Improved spectroscopic techniques, faster data processing algorithms, better trajectory modeling. These developments enhance our ability to study everything from near-Earth asteroids to distant galaxies. The international collaboration achieved for 3I/ATLAS sets precedents for future crisis response. When the next interstellar visitor arrives, and statistics suggest one appears every few years, we'll be better prepared. Protocols established, networks activated, instruments ready. Public engagement with 3I/ATLAS, despite the signal mythology, has been extraordinary. Millions of people have learned about orbital mechanics, spectroscopy, and planetary formation. The visitor has inspired students to pursue science careers, amateur astronomers to contribute observations, and citizens worldwide to contemplate our cosmic context. And it's just the beginning of what promises to be an era of interstellar discovery. The Vera Rubin Observatory, under construction in Chile's Atacama Desert, will transform interstellar visitor science from rare accidents into routine discoveries. Beginning operations in 2025, its 8.4-meter mirror and 3.2 gigapixel camera will survey the entire visible sky every 3 nights, detecting objects far fainter than current surveys can see. Conservative estimates suggest Rubin will discover 10 to 20 interstellar objects annually. Optimistic projections reach 70 per year. Within a decade, we'll have a statistical sample large enough to understand the true diversity of interstellar debris, moving from anecdotal observations to population studies. Dr. Lisa Park leads planning for the Legacy Survey of Space and Time. We're preparing for a flood of discoveries. Each interstellar visitor will be detected earlier, tracked longer, and studied more comprehensively than 3 I/ATLAS. We're building the infrastructure for an entirely new field of astronomy. The Comet Interceptor mission, launching in 2029, represents humanity's first dedicated attempt to encounter an interstellar visitor. The spacecraft will wait at the Sun-Earth L2 Lagrange point, 1.5 million kilometers from Earth, ready to redirect toward targets of opportunity within months rather than years. Think of Comet Interceptor as a rapid response team for cosmic emergencies. When the next Oumuamua or 3 I/ATLAS appears, the spacecraft can intercept it, capturing high-resolution images, analyzing composition, and potentially collecting samples of actual interstellar material. Ground-based preparations are equally ambitious. The extremely large telescope, with its 39-meter mirror, will resolve details on interstellar visitors that current telescopes can't detect. Spectroscopic capabilities will identify trace molecules, isotope ratios, and potentially biosignatures if they exist. Radio telescope arrays are implementing new protocols for rapid response. When Rubin detects an interstellar visitor, radio observatories worldwide will automatically begin monitoring for emissions, whether natural or otherwise. The lessons from 3 I/ATLAS's false signal rumors have improved verification procedures. Dr. James Chen coordinates the Interstellar Object Working Group. We're creating decision trees for every scenario. Chemical anomalies, trajectory deviations, unusual emissions will have protocols ready. No more scrambling like we did with Oumuamua and 3 I/ATLAS. Data management infrastructure is scaling to handle the expected flood. Each interstellar visitor generates terabytes of observations across multiple wavelengths. Cloud storage, distributed processing, and machine learning algorithms will help researchers extract meaningful patterns from enormous datasets. International agreements are evolving to facilitate rapid response. Telescope time allocation, funding mechanisms, and data sharing protocols are being negotiated now before the next crisis. The goal is seamless global coordination within hours of discovery. Public communication strategies have been refined based on 3 I/ATLAS experience. Science communicators are developing templates for explaining natural phenomena that might seem artificial, addressing conspiracy theories before they spread, and maintaining public engagement without sensationalism. Educational materials are being prepared for the expected discoveries. When Rubin finds its first interstellar visitor, classrooms worldwide will have age-appropriate resources to explore the science. The goal is inspiring the next generation while preventing misinformation. The search for technosignatures continues with renewed sophistication. While 3 I/ATLAS proved natural, the possibility of artificial interstellar objects remains. SETI protocols have been updated to handle rapid verification of potential signals from fast-moving targets. Sample return missions are being conceptualized for the 2030s and beyond. If we could capture even microscopic particles from an interstellar visitor, laboratory analysis could reveal isotope ratios, mineral structures, and potentially organic molecules from another star system. The statistical power of multiple discoveries will answer fundamental questions. Are CO2-dominated objects common or rare? Do most interstellar visitors come from the thick disk or elsewhere? Is there a size distribution suggesting specific ejection mechanisms? Dr. Anderson anticipates revolutionary discoveries. With dozens of examples, we'll identify patterns invisible in single objects. We might discover distinct populations, chemical families, or even evidence for specific stellar sources. The galaxy is full of wanderers, and we're finally ready to meet them properly. The word alien perfectly describes 3I/ATLAS, not because it's artificial, but because it's genuinely foreign to everything in our solar system. This visitor carries chemistry from another star, physics from another epoch, and history from before our world existed. Its natural origin makes it no less extraordinary than if it were an engineered probe. Consider what alien truly means: unfamiliar, foreign, belonging to another place. 3I/ATLAS, formed around a star we'll never see, in conditions we can only model, from materials processed by stellar nuclear reactions different from our sun's. Every molecule in its nucleus is alien in the most literal sense. Dr. Robert Martinez studies isotope ratios in meteorites. Solar system materials show specific isotopic signatures from our sun's formation environment. 3I/ATLAS should carry completely different ratios, fingerprints of wherever it formed. We're looking at genuinely alien chemistry, just not artificial chemistry. The carbon dioxide dominance tells us about alien planetary formation. Somewhere in the galaxy, protoplanetary disks create objects with inverted volatile ratios compared to our comets. These environments might be common. We simply hadn't sampled them until 3I/ATLAS arrived. Think about the journey this material has taken. Atoms forged in an alien star's core, expelled in stellar winds, condensed in an alien protoplanetary disk, assembled into a comet, ejected into interstellar space, and wandering for billions of years before arriving here. Each atom has a story spanning cosmic time. The preservation of structure after such a journey amazes researchers. Despite radiation that would sterilize any biology, temperatures approaching absolute zero, and impacts from cosmic dust, 3I/ATLAS maintains enough integrity to produce its enormous coma. This durability reveals how matter behaves under extreme conditions we can't replicate. Timescales add another dimension of alienness. 3I/ATLAS is older than Earth's oceans, older than our continents, possibly older than our planet itself. It represents not just another place, but another time, carrying information about the galaxy's youth frozen in its ice. Dr. Sarah Johnson models galactic chemical evolution. 8 billion years ago, the galaxy contained different element abundances. Fewer supernova generations meant less enrichment in heavy elements. 3I/ATLAS might preserve that primordial chemistry, showing us what planetary materials looked like in the early galaxy. The dynamics reveal alien gravitational environments. Whatever stellar system ejected 3I/ATLAS must have contained massive planets creating gravitational chaos. The ejection velocity tells us about close encounters with gas giants, stellar companions, or other massive bodies we can only imagine. Even the concept of comet becomes alien when applied to 3I/ATLAS. Our comets follow elliptical orbits, returning periodically to the inner solar system. They're family members, however distant. 3I/ATLAS is a true stranger, passing through once on a journey without return. The extended coma demonstrates alien physics, not violations of natural law, but extreme conditions creating unexpected phenomena. Whether through fragmentation, explosive sublimation, or unknown mechanisms, 3I/ATLAS shows that our laboratory experience doesn't encompass nature's full repertoire. Biological implications fascinate astrobiologists. If 3I/ATLAS carries organic molecules, and many comets do, they formed in alien chemistry under alien radiation around an alien star. These organics might include molecular structures impossible in our solar system, expanding the potential diversity of prebiotic chemistry. Dr. Chen speculates on panspermia implications. If microscopic life can survive interstellar journeys, 3I/ATLAS could theoretically carry alien microorganisms. Not intelligent signals, but actual alien biology. Dormant in the ice. We can't detect such life with current observations, but the possibility exists. The visitor challenges Earth-centric thinking about planetary science. Our models assume solar system conditions, solar composition, solar history. 3I/ATLAS forces us to generalize, to consider how planets form across the galaxy's diverse stellar environments. Cultural concepts of alien typically invoke intelligence, technology, intent. But 3I/ATLAS shows that natural objects can be profoundly alien without any artificiality. What it means for planet formation theories requires complete reconsideration of our models. Every astronomy textbook written before 2017 is now obsolete. The discovery of interstellar visitors, culminating with 3I/ATLAS's bizarre chemistry, has forced a complete reconceptualization of planetary science. Chapters on comet composition, planetary formation, and galactic material exchange need comprehensive revision based on these cosmic wanderers. The traditional model was elegant in its simplicity. Comets form in the cold outer regions of protoplanetary disks, incorporating mainly water ice with traces of other volatiles. They preserve the primordial composition of the solar nebula, serving as frozen time capsules. This model worked perfectly until 3I/ATLAS arrived with its inverted chemistry. Dr. Jennifer Williams leads textbook revision at MIT. We're not just adding footnotes about interstellar objects. We're fundamentally restructuring how we teach planetary formation. The diversity revealed by 3 visitors suggests our solar system might be unusual rather than typical. Think of it like discovering new continents after centuries of believing Earth contained only one landmass. The maps don't just need updates, they need complete redrawing. Every assumption about typical planetary systems requires re-evaluation. The carbon dioxide dominance of 3I/ATLAS suggests formation environments we hadn't seriously considered. Textbooks now must include sections on CO2 snowlines, carbon-enhanced stellar environments, and volatile chemistry in high-carbon systems. These aren't exotic exceptions, but potentially common conditions we happen to miss. Formation temperature regimes require expansion. We understood water, CO2, and CO snowlines in our solar system. But 3I/ATLAS hints at intermediate zones where unusual chemistry dominates. Future planetary scientists must learn about chemical gradients we're only beginning to map. The size distribution of interstellar objects challenges models of planetary system clearing. If objects like 3I/ATLAS are common, then stellar systems must eject far more material than we calculated. This affects estimates of planet formation efficiency, disk mass requirements, and the total solid material in the galaxy. Dr. Michael Anderson revises dynamical models. Every planetary system is now understood as both isolated and connected. Isolated during formation, but exchanging material with other systems over billions of years. It's a fundamental shift in perspective. Cometary activity models need complete overhaul. The extended coma of 3I/ATLAS demonstrates that small nuclei can affect enormous volumes through mechanisms not in current textbooks. Whether through fragmentation, amorphous ice transitions, or explosive sublimation, we must teach phenomena we don't fully understand. The preservation of volatiles during interstellar travel rewrites chapters on ice physics. Textbooks assumed cosmic radiation would destroy or heavily modify ices over millions of years. 3I/ATLAS proves that complex volatile chemistry can survive billions of years, requiring new sections on radiation processing and ice stability. Galactic archaeology becomes a required subject. Understanding interstellar visitors requires knowledge of stellar populations, galactic chemical evolution, and the dynamic history of star formation. Planetary science can no longer be separated from galactic astronomy. Statistical frameworks must be introduced earlier in curricula. With single examples like Oumuamua, statistics seemed premature. With 3 visitors showing 3 different chemistries, statistical analysis becomes essential. Students must learn to distinguish between individual peculiarities and population characteristics. Laboratory analog studies gain new importance. We can't visit other stellar systems, but we can simulate their chemistry in laboratories. Experiments with exotic ice compositions, unusual formation temperatures, and extended radiation exposure become standard rather than specialized research. Dr. Park describes pedagogical challenges. How do you teach about objects when each new discovery contradicts the previous one? We're moving from teaching facts to teaching uncertainty, from memorizing properties to understanding processes. The timeline of solar system history needs adjustment. We previously taught formation and evolution as isolated processes. Now we must include regular interstellar visitor passages, potential material exchange, and the possibility that Earth itself has encountered thousands of objects like 3I/ATLAS. Why normal might not exist becomes a crucial lesson for future scientists. The galaxy is not a collection of isolated stellar islands, but an interconnected web where material flows between stars over billions of years. 3I/ATLAS represents just one thread in this vast network of exchange, proving that stellar systems share their chemistry, their history, and potentially their biology across interstellar distances. Current models suggest every star ejects millions of comet-sized objects during planetary formation. Jupiter-mass planets scatter smaller bodies like gravitational catapults, launching them into interstellar space. With 400 billion stars in our galaxy, the wandering population must number in the septillions, more interstellar objects than stars themselves. Dr. Lisa Chen models the interstellar medium. We're swimming in a sea of cosmic debris we can't see. For every 3I/ATLAS we detect, millions pass through the outer solar system unnoticed. Earth has probably encountered hundreds of thousands of interstellar visitors over its history. Think of galactic material exchange, like ocean currents carrying seeds between islands. Most seeds die in salt water, but occasionally one reaches shore and sprouts. Similarly, most interstellar objects pass through stellar systems without effect, but rare encounters might transfer material or even life between worlds. The slow exchange rate has profound implications. If typical interstellar objects travel at 30 kilometers per second, crossing the galaxy takes 100 million years. But with septillions of objects and billions of years, even unlikely exchanges become statistically certain. Every stellar system has probably received material from thousands of others. Earth itself must have encountered numerous objects like 3I/ATLAS throughout its history. Some passed harmlessly through the outer solar system. Others might have impacted, delivering alien chemistry to our world. The late heavy bombardment 4 billion years ago could have included interstellar impactors. Dr. Robert Thomson calculates impact probabilities. Once every 100 million years, Earth probably collides with an interstellar object. Most are small, but they deliver genuine alien material. We might have fragments of other stellar systems in our geological record. The chemical diversity revealed by 3 interstellar visitors suggests the galaxy contains a vast library of planetary materials. Each stellar system contributes its unique chemistry to the wandering population. Over cosmic time, this creates a slowly mixing reservoir of diverse compositions. Panspermia, the hypothesis that life spreads between worlds, gains credibility from confirmed material exchange. If microorganisms can survive in cometary ice, and if comets regularly travel between stars, then life could propagate throughout the galaxy without any intentional mechanism. The preservation demonstrated by 3I/ATLAS supports this possibility. Despite billions of years in interstellar space, it retained volatile ices and potentially organic molecules. Dormant microorganisms, if they existed, might survive such journeys in crystalline ice or within rocky matrices. Dr. Martinez examines extremophile survival. We know Earth organisms can survive space exposure for years. Whether they could survive for millions of years remains unknown, but 3I/ATLAS proves that complex chemistry can persist for billions of years. The network topology matters for galactic ecology. Stars don't randomly exchange material. Gravitational dynamics create preferred pathways. Stellar streams, moving groups, and spiral arm passages create highways for interstellar exchange. Some regions might be highly connected, while others remain isolated. Our solar system's position in the galaxy affects its connection to this network. We orbit in the galactic suburbs, between spiral arms, in a relatively quiet region. This might limit our interstellar encounters compared to stars in denser regions or near the galactic center. The time dimension adds complexity. Stars that exchanged material billions of years ago have since separated by thousands of light years. 3I/ATLAS might come from a stellar system now on the opposite side of the galaxy, making backtracing impossible. Future discoveries will map this cosmic web in detail. As we detect more interstellar visitors, patterns will emerge. Chemical families suggesting common origins, trajectory correlations revealing stellar streams, and size distributions indicating ejection mechanisms. The next one is already on its way, perhaps multiple visitors approaching from different directions. As 3I/ATLAS fades into the darkness beyond our telescopes, carrying its ancient secrets back to the interstellar void, we're left with a choice about how to interpret its visit. We can fear the unknown, spinning conspiracies about hidden signals and alien surveillance, or we can embrace wonder at a universe far stranger and more magnificent than human fiction has ever imagined. The truth about 3I/ATLAS surpasses any manufactured mystery. Here was a fragment of another star system, older than Earth itself, that traveled billions of years to briefly grace our skies. It carried chemistry that shouldn't exist, created phenomena that challenged physics, and connected us tangibly to the galaxy's deep history. No artificial signals were needed to make this extraordinary. Dr. Sarah Mitchell, who spent months analyzing 3I/ATLAS data, reflects on the experience. The real message wasn't electromagnetic, it was chemical and kinematic. The universe told us that stellar systems share material across impossible distances, that chemistry varies more than we dreamed, that we're part of something vast and ancient and ongoing. Think about what we actually discovered versus what people feared or hoped. No alien transmissions, but genuine alien chemistry. No artificial probe, but natural processes we didn't know existed. No threat to Earth, but a challenge to every assumption about planetary formation. Reality exceeded fiction by being simultaneously stranger and more comprehensible. The human tendency to see patterns, purpose, and communication in random phenomena isn't a flaw. It's the same cognitive ability that lets us do science. We notice 3I/ATLAS because we're pattern seekers. We studied it because we're curious. We learned from it because we can distinguish real patterns from imagined ones. The social media mythology around 3I/ATLAS reveals something important about human psychology. We desperately want connection, meaning, and confirmation that we're not alone. These desires are beautiful, even when they lead to misinterpretation. The search for signals that didn't exist came from the same wonder that drives legitimate science. Dr. James Anderson addresses public misconceptions. People weren't wrong to be excited about possible signals. They were wrong about the specific claims, but the excitement itself was appropriate. 3I/ATLAS deserved wonder, just for different reasons than viral posts suggested. The scientific process worked exactly as designed. Extraordinary claims about artificial signals were made, tested, and falsified. Natural explanations were proposed, refined, and confirmed. The self-correcting mechanism of science transformed confusion into knowledge, mystery into understanding. International cooperation achieved for 3I/ATLAS proves humanity can unite around cosmic curiosity. Despite political tensions, economic competition, and cultural differences, observatories worldwide coordinated seamlessly. The universe doesn't care about borders, and neither did astronomers studying this visitor. Educational benefits will persist for generations. Millions learned about spectroscopy, orbital mechanics, and interstellar space. Students who might never have considered astronomy discovered passion for science. The false rumors prompted real learning as people sought to understand what was actually happening. The preparation for future visitors improves because of 3I/ATLAS. We've learned what observations matter most, how to coordinate rapid response, and how to communicate findings without spawning mythology. The next interstellar object will be studied more efficiently and understood more quickly. Dr. Chen offers perspective on cosmic loneliness. Whether or not intelligent aliens exist, 3I/ATLAS proves we're connected to the cosmos in ways we're only beginning to understand. Material exchange between stars means we're not isolated. We're part of a galactic ecosystem. The wonder of 3I/ATLAS lies not in imaginary signals, but in confirmed realities. Interstellar space isn't empty, but populated with wanderers. Chemistry varies enormously between stellar systems. Small objects can create enormous phenomena. Ancient ice preserves information across cosmic time. The universe doesn't need artificial embellishment to inspire awe. Natural processes create structures larger than planetary orbits, preserve chemistry for billions of years, and exchange material between stars. Reality is sufficient for wonder. 3I/ATLAS won't broadcast to aliens, but it already sent us a message. The cosmos is stranger and more wonderful than our fantasies. As this ancient traveler continues its eternal journey, it leaves behind not disappointment that it wasn't artificial, but gratitude that the natural universe